In order to understand hypothesis testing, let's return to the hypothetical example of the researcher who's comparing the Magic Math program among 7th grade students to the standard curriculum. She wants to test whether it's superior to the standard curriculum. The alternative hypothesis would be that Magic Math leads to increased math scores for 7th grade students. The null hypothesis is that participation in the Magic Math program does not lead to increased math scores for 7th grade students. Let's pretend that we tried this in 2 different school districts. What did we find? For this example, let's say the average score for Magic Math was 19.5 points, while the average score for the current program was only 19.3 points. What do we conclude? Magic Math is a little higher, but it's not much. Maybe it's just due to one student who got lucky on the test. Is this a real difference or just random chance? This is where inferential statistics come into play. Inferential statistics can tell us how likely it is, if the null hypothesis is true, that we would see a difference this big just by chance. If Magic Math doesn't lead to higher math scores, inferential statistics can tell us how likely it is that we would have seen a difference of 0.2 of a point simply by chance. You can think about it this way. Let's say that I have a coin and it has both a head side and a tail side, and we start making bets based on whether it lands heads, I win, or tails, you win. Of course, it's my coin, so you have to trust me that it's not weighted. In this case, the null hypothesis is that the coin is not weighted and is fair. Nothing funny's going on. Everything's fine. The alternative hypothesis is that the coin is weighted. I'm cheating. Something funny's up. Everything's not fine. Of course, you assume the null is true. I'm not cheating. And you really, really want to be convinced otherwise before you reject the null and call me a cheat. The first flip lands heads, so I win. Would you call me a cheater? Probably not. That would happen half the time anyway. The second flip is also heads. 2 wins in a row for me. Would you call me a cheater now? I would hope not, because that would still happen 25% of the time. What about 6 out of 10 flips? I'm a little ahead, but it's still very believable. You probably want to be more confident before calling me a cheater. On the other hand, if we flip the coin 100 times and 90 of the times it came up heads, the chance of that randomly happening is so small, way less than 1 in a million times, that you should be much more comfortable saying I'm cheating. At some point, you're going to say, hold on a minute, there is no way that coin is fair. So returning to our Magic Math study, the question's this. If the null hypothesis is true and there is no difference between the programs, would the Magic Math program have a 0.2 of a point difference so rarely that one is comfortable rejecting the null hypothesis? Is this difference so unlikely to happen if the null hypothesis is true that the null hypothesis almost certainly is not true? At the risk of getting a little more technical, one thing that inferential statistics can do is estimate what would happen if a researcher did this study over and over and over an infinite number of times with similar but different samples from the same population. Even if the Magic Math program has no effect at all, sometimes students in the program are going to score higher. Sometimes they're going to score a lot higher. If Magic Math has no true effect, how often would the Magic Math students just happen to end up with a mean that was 0.2 of a point higher than the students in the standard curriculum? Would we see a difference this larger 20% of the time, 10% of the time, 1% of the time? If it would have happened 20% of the time if the null hypothesis were true, and the researcher still goes ahead and rejects the null hypothesis anyway, they risk making a type 1 error 20% of the time. That's probably way too often for comfort. And this small difference that we're seeing may well just be a random blip. On the other hand, if one would have seen a difference this large only 1 in 1,000 times when the null hypothesis was true, it looks a lot more real. If it only happens 1 in 1,000 times, or 1/10 of 1% of the time if the null is true, the null probably isn't true. I mean, what's the chance we would have just happened to stumble on that 1 in 1,000 samples that would have given us this result? In that case, the researcher can reject the null hypothesis and conclude that magic math does seem to help students improve their scores. So, what does it take to reject the null hypothesis? This is where the alpha level comes in. Alpha, or the alpha level, is the probability of making a type 1 error. Researchers decide what their alpha level will be before they ever begin their study, and it's based on how comfortable or uncomfortable they are in making a type 1 error. As a rule, behavioral researchers hate type 1 errors so much that they set alpha to be equal to 0.05. In other words, they only want to make a type 1 error 5% of the time. As a result, they need to see an effect that is so large it would have happened less than 5% of the time if the null hypothesis were true. If that happens, the researcher concludes that the results were so unlikely if the null were true that the null probably can't be true, so they reject it. Notice that alpha has nothing to do with our data. It's not something that we calculate from our data. Before we ever begin our study, we should determine how comfortable we are making a type 1 error and set our alpha level before we've ever collected our first piece of data. Now, in addition to the alpha level, there's what's called the p-value, which is the probability that one would have seen an effect this large or larger if the null hypothesis were true. For example, let's say we're comparing two groups and we obtain a p-value of 0.01. That indicates that if the null hypothesis were true, we'd see a difference that big or larger about 1% of the time, 0.01. Now, the alpha level and p-value are related, but they're different. And if you find that difference a little confusing, it may help to think of the alpha level as a line in the sand that's drawn by the researcher that you must cross in order to reject the null hypothesis. The p-value then indicates whether your results have in fact crossed that line. To quote Quark from Star Trek,
"The line has to be drawn here, this far and no further."
So, the alpha level is set before the study begins and is based on how comfortable the researcher is making a type 1 error. It's the line in the sand that the researcher draws and says, if the results are so unlikely that they cross this line, I'll reject the null. The p-value is calculated based on the data that the researcher collects and indicates the likelihood that the given results would have happened if the null were true. It's the p-value that either crosses that line or fails to cross that line. Now, this is important. A complete, full definition of the p-value is that it's the probability of obtaining a result as extreme or more extreme than what was observed in the direction of the alternative hypothesis, assuming the null hypothesis is true. Now, notice the last 2 points in the definition. First, by extreme, we mean a result, in this case a mean, that is this far or farther out in whatever direction the alternative hypothesis is pointing us. And importantly, The p-value is always calculated assuming the null hypothesis is true. We're estimating how likely it is that we would have seen something this extreme or more extreme if the null hypothesis is true. Let's assume that the researcher only wants to commit a type 1 error 5% of the time, and so the alpha is 0.05. If the p-value is greater than the alpha level, for example, if p equals 0.12, indicating that there's a 12% chance that a difference this large would have been seen if the null hypothesis were true, then the researcher will fail to reject the null hypothesis. Again, if the p-value is greater than the alpha level, the researcher will fail to reject the null hypothesis. On the other hand, if the p-value is less than the alpha level, then the researcher will reject the null hypothesis. For example, let's stick with the researcher only wanting to commit a type 1 error 5% of the time, and so the alpha is 0.05. But now assume that the p-value is 0.02, indicating that there is a 2% chance that a difference this large would have been seen if the null hypothesis were true. 0.02 is less than the alpha of 0.05, and so the null hypothesis is rejected. Researchers want the p-value to be less than the alpha level because it allows them to reject the null hypothesis. But where do p-values come from? That's where test statistics come in. But let's stop here for now and continue on that topic in our next video in this series.